the name of Allah, the most merciful and the Almighty. My name is Hamza Ahmed Qureshi, and today is our FIP progress presentation. The title of our FIP project is Experimental and Numerical Modeling of Helical Files Subjected to Axial Loading. These are the contents of our presentation: members profile, program statement, literature review, work plan, instrumentation, model testing, results, references, and question answer session. Member profile. This slide includes name of the member, section, row number, and registration number. Now coming towards the problem statement, as we all know that the population of the world is increasing day by day. According to UN 2015 report, the population of the world is expected to be 8.5 billion by the end of 2030. So what is happening that the demand on the soil is increasing day by day. Real estate and the government, they are moving from 3-story to 2-story building to multi-story high-rise building. So we can say that the need of deep foundation will increase more in the coming era. So now what the problem is, we know that as an engineer, we prefer our project to be cost effective, less time consuming, and fast installation. So the developed countries like USA, Canada, Japan, New Zealand, they are using helical piles as a deep foundation technique. However, in Pakistan, we are still using conventional piles. So the prime objective of our FIP project was to conduct model tests on helical piles and compare its axial capacity with the conventional piles. Those model tests which were run by Irfan Jamil sir in his PhD project. The second objective was to find the effect of number of helix on the axial capacity of helical piles. Third objective was to numerical modeling of helical piles using Texas 3D software. Now literature review. Helical pile. It is a prefabricated steel pile which consists of galvanized steel shaft, either square or circular in shape, having single or multiple helix attached to it. This was for the first time used by Irish civil engineer Alexander Mitchell in 1836 in the foundation of Lighthouse. Now, there is a question that if conventional piles are available, so why these developed countries, they are using helical piles? So it is because of their greater axial capacity, greater lateral capacity, better seismic performance, ease of installation. Its installation is vibration free. You don't need to hammer the pile, you just need to apply torque with the help of hydraulic machine. Cost effective. A report published by Almeta Piling Incorporation in 2015 stated that it is cost effective than conventional piles. Instant loading. Today you install the pile and on the same day you put load on it. Lower mobilization cost. Here you can see the helical pile, its shaft, and it is a double helical pile. Now real case studies. Here we include two real case studies just to show our viewers that helical pile is practically applicable. In 1997, Camp Children Center, Colorado was constructed in USA, and in 2008, 3 multi-story hospital Woodstock, Ontario was constructed. So these were some of the case studies. Now exact capacity of helical piles. Several researchers conducted full-scale load tests on helical piles, and they concluded that more axial capacity than conventional piles. Similarly, some of the researchers conducted model tests, and the results were the same. Now, number of helix. Researchers said that increasing the number of helix increased the axial capacity of helical piles, and that what we saw in our result when we perform our model test. So this was all from my side. Now, thank you for listening. I would like to invite Hamza Khan to kindly come and present his part of presentation.
Thank you, Hamza and Qureshi, for inviting me. Now, this is my part of presentation once again. Our FIP project is divided into two parts. The first part is the experimental testing, and the second part is the numerical modeling. In the first part is the experimental testing. First we do instrumentation, in which we bought the files and get fabricated. After that we do model testing, and after model testing we do the data interpretation. After data interpretation we conclude the results and draw graphs. This first part is completed, and the second part, which is the numerical part, is yet to be completed. Now the instruments, as you can see, that these are the instruments which can be further explained on the next slide. So first, as you can see in the image, that the side lock, it is basically an iron sheet 76 millimeter thickness, and the dimensions are the 4 × 3 × 5 feet. Second one is the LVDT, linear variable displacement transducer. It is basically to find the displacement or settlement in the pile rock. And in our experiment we use 4 LVDTs, and this is the image of now load cell. As you can see in the image, that this is the load cell, and it is a device used to measure the implied load. The signals from the load cell were received by the data logger. Data logger, this is the image of data logger. It is basically to collect the data from the LVDTs and the load cell, helical pile, and pile rock. These are the helical piles in which 18 helical piles were fabricated, in which 9 were single helix and 9 were double helix. And the upper part is the pile graph, which is made up of aluminum, and the dimensions are 1 plus 1 feet. These are the dimensions in which length is 18 inches, external shaft diameter, internal shaft diameter, helix diameter, thickness of the thread, pitch of the helix, distance of the helix from the bottom of the pipe, and spacing between the two helixes is 3.7 inches. And this is a standing rod, which we placed the standing rod on the load cell in the experiment, which will be further explained by Nancy Khan. And these are the vertical load. So we place all the load security on the center of load cell. So we use this instrument as standing rod. Now air pulviator, it is basically a device called mobile pulviator, which was used to maintain the relative density of sand during the test, and this device was used to pour sand in the box. Now this is all from my side. Now I would like to invite Adnan Salim Khan to present his talk.
So thank you, Hamza Khan, for inviting me. Now I will proceed with my part of the presentation, which is model testing. So we performed a total of 6 model tests, out of which 3 were for single helical piles and 3 were for double helical piles with different configurations. As you can see the pictures which are attached at the side. So this is the layout. This is the layout of our model testing 4 pile configuration. Each pile is having a spacing of 5 inches between them, center to center distance. This is the configuration for 6 pile, and this is the configuration for 9 pile. So I will explain the procedure for one of the configuration, and we repeated the procedure for the other configuration. Means the procedure was same for all the configuration. So first of all, we remove the soil from the sandbox. Then with the help of air pulviator, we poured the soil from a certain height, which was 18 inches. Once we filled the box up to 3-4 parts, then we placed the helical pile raft model, and we started the air pulvation again. So when half piles were dipped in the sand, so then we removed the raft and started the air pulvation again. So once we completely submerged the piles in the sand, so we connected the raft again to the piles. Now this setup was completed to further proceed the experiment. Now we placed 4 LVDTs on the corners of in the vertical direction, and we connected them with the data logger. Similarly, we placed a load cell on the raft and connected it to the data logger. After that, we placed the standing rod and placed the load cell on that. So once data logger was connected, so we connected them with the software. Then we started the software and placed the load one by one. After putting all the loads, which was 512 kgs, so we stopped the software and recorded our values. So our procedure was completed here. Now I will explain the model testing with the help of this schematic view. First we emptied the soil box, consider the air pulvation is then we placed the pile raft over it. After that we placed the load cell over it, and then we placed LVDTs at each corner in vertical direction. We connected those LVDTs with the data logger. After that we connected the load cell with the data logger. So then we connected the data logger with the computer having MATLAB software. So then we turned on the software and placed the load one by one in order at an increment of 16 kgs. After that, MATLAB gave us the values, we recorded that values, and we turned off the software. So this is the picture which we performed the test. These are the LVDTs. 4 LVDTs were connected at each corner. This is the pile raft. These were the loads. We placed them one by one at an increment of 16 kgs, and this was the data logger, and it in turn was connected with the software. So this was all from my side. Now I would like to invite Muhammad Ali to further proceed his part of presentation. Thank you.
Thank you, Adnan Salim Khan. So my part of the presentation is the results and the conclusion of our experiment. So we discussed 3 cases, that is the 4 pile raft, the 6 and the 9 pile raft configuration. So let's talk about the 4 pile raft first. So we drew this graph in Axial. As you can see, there are 3 types. First is the conventional. We increased the loads up to 5,000 meter, and corresponding are the values for settlement. For example, for conventional it was up to 7.6 millimeters. For single helix it was about 5.2 millimeters, and for double helix it was about 4.8 millimeters. So we also found out the percentage reduction in settlements for helix to conventional piles, and in case of the single helix it was 30.64%, and in case of double helix it was 37.48% reduction. case of 6-pi rod configuration, again, we did the same procedure, and for 5,000 Newton vertical load, you can see the corresponding reduction. There was 6.71 millimeter settlement for conventional piles, 4.3 millimeters in case of single helix, and 4 millimeter in case of double helix. Similarly, for the 9-pi rod configuration, we had the same observations that by adding the helix, the settlement reduces. As you can see again, in case for conventional, it was around 5.3 millimeters, and then when we use single helix, it reduced to 3.3 millimeters, and in case of double helix, the settlement was around 3 millimeters. So we draw a couple of conclusions from our experiment. So we found out the average value of, for the single helix, the average value of the percentage reduction in settlement. So in case of single helix, the average value was around 34.3%, and in case of double helix, the value of the reduction in settlement was around 41%. So hence, helical piles have greater axial capacity than conventional piles, and increasing the number of helix increases the axial capacity of helical piles. And these are the references of our presentation. And this is the end of our presentation. Thank you. If you have any questions, you're most welcome.